fine.
Yeah, the ownership.
Sorry, updates for Georgie.
This is my cat. Our friend Courtney is watching her.
So it's mostly sleeper, baby, and then
she's like super curious and she has a ton of energy. So she's affectionate when she gets tired, but usually she's too busy like playing, doing stuff. She's like a year and a half. So pretty young, but yeah.
yeah, and then there are like all sorts of deviations. The one you're like,
It's not looking, I'm still falling asleep.
Start? Okay. So is the mic working? Yeah, can you hear? Okay. So I'm going to finish up some odds and ends because some of the topics which I wanted to discuss we'll certainly not have any time for. And one thing I forgot to mention is that the Lesouche lectures have a whole bunch of homework problems in there. So if you're bored, you can try doing them. And the Lesouche students actually wrote up detailed solutions to the problems which are on the archive. So you can access that as well and see the solutions. And so there's like 50 pages of solutions or something teched up.
On the same document?
No. So I can, yeah, maybe what I'll do is I have it downloaded. I can just post it to the wiki. So they wrote up solutions to all the homeworks from all the Lesouche lectures. But it turns out of 65 pages of solutions, 50 pages are from my homeworks and the 15 are for the remaining 10 lecturers. But anyway, but it's you know, in gory detail, all the aspects of EFT. So if you don't want to go hiking, you can do the homework instead. All right. OK, so let me finish up with a few odds and ends from last time. So we were considering what I call the full theory in Coates integrals. And if I expand it out in the low scale, and I'll stick with one loop, you can get divergent pieces, which I'll explain this in a second. So some possible UV divergence, some possible IR divergence, and dimensional irregularization can regulate both of them, and some possible constant terms. And you can get IR divergences because you've expanded out in M, and maybe M regulated some of the IR divergences. Now, if you do the EFT expansion, again, expanding in little m, same expansion, we saw that it was 0 because everything was scaleless. But it turns out, and it's 0 in a funny way. And I'm going to write it this way, and you'll see why. OK. And I can't hear you. So in the kind of theories like the weak interactions at one loop, you would only get first order poles. But if you do theories like SCT, you will get 1 over epsilon squared poles. And then there will be a log in the anomalous dimension. But let me stick with more like the in code standard EFTs. Yeah. And then there are some subtleties as to whether the epsilon squared should be treated as UV and IR and things. I don't want to get into any of that mess. Yeah. Yeah.
So you said this is 0 because it's scaleless. Why is that?
So I'm going to, yeah, so that's what I wanted. So the kind of integral which you get is d4k over k to the 4th. So that's scaleless, and it's log divergent. And I can write that as d4k over k to the 4th, k squared over k squared minus m squared over k squared minus m squared, which is just 1. So it's the same integral. This piece is UV divergent, but not IR divergent. It's got, in the IR, this extra k squared makes it finite in the IR. And this one is IR divergent. So let's say UV divergent. This one is IR divergent, but not UV divergent, because the 1 over extra k squared minus m squared makes it finite in the UV. Goes like 1 over k to the 6. Now you can do both of these integrals in dim reg. You'll get some 1 over epsilons and finite parts. You add the two pieces together, you'll get 0. But I can think of this, so when I do dim reg, I get 1 over epsilons and log m's and whatever. So for this first part, I'm going to call, you get I over 16 pi squared. And there's a 1 over epsilon. This is what you get, 1 over epsilon minus. You also get constants, which also cancel. But I'm going to just focus on the 1 over epsilons, the divergent part. And because this is UV divergent, this singularity is a UV singularity. And the other one's an IR singularity. So you get 0, but in the form of 1 over epsilon minus 1 over epsilon. You have to be a little bit careful, because we're working in D as 4 minus 2 epsilon. So it's not like you can really distinguish what the UV and the IR are, but you have to sort of analyze the integral and figure it out. Now, there's a big difference between UV and IR singularities. In a field theory, UV singularities are canceled by counterterms. IR singularities are not. You don't add any counterterms. They're an indication that maybe you're not calculating the right quantity. So the classic example is you go E plus E minus to QQ bar. Well, usually what you do is you divide this by E plus E minus to mu plus mu minus. And that's what's called R. And at tree level, so you're working at high energies, massless quarks. You treat the muon as massless, then basically all you're getting here is the quark charge squared. I'll just call that Q squared. And times 3 for the number of colors. So that's like the lowest order value for R. Because if you had high energies, the quark mass and the muon mass, everything, it doesn't matter. But when you go to next order, you get this kind of diagram, where this is a gluon now. And so let's call this amplitude A0 for tree level and A1 at one loop. So the cross section, E plus E minus to QQ bar, has an A0 plus A1 absolute. You have to add the amplitudes. Within quantum mechanics, you first add the amplitudes and then square. And there's a cross term between A0 and A1, which is order alpha, because this A1 is alpha times A0. And that's infrared divergent. You also have a real process where you emit a gluon, which is EE to QQ bar glue. And this is this doesn't interfere with that process, because the final state's different. So you just square this, you get two couplings, and this is also order alpha. This is also infinite. And you add the two together, and you get a well-defined number, which is 1 plus alpha s over pi. And then I think people have calculated this at least to 4-loop order. Okay, but there's a cancellation between real and real singularities and virtual singularities. And what's hard in collider physics is not, even though people will say, you have these so many diagrams and have to calculate them all and so on, the problem is not calculating the amplitude. The problem is to get a physical LHC cross-section. If you work to some order, you have to cancel the real and virtual processes. So at next order, you'll have two emissions, an interference of a diagram with one emission and one virtual, and then two virtuals. And as you go to one higher order, you'll have three virtuals, two virtuals, and one real, et cetera. And you can't do this numerically because these are infinite, and you have to figure out how the cancellation works before you do the phase space integrals. And phase space integrals are really hard. So these infrared divergences are some, maybe you're calculating here something which is infrared divergent, like this amplitude. It's fine. You can then combine it with something else to get a physical process. But you do not cancel these IR divergences by counterterms. Now, I wrote it in this way because by construction, the EFT has the same infrared as the full theory. Therefore, whatever the IR singularity is here is the same in the EFT. So this B is the same as that B. It has to be. Now, because the EFT is scaleless, and this answer is 0, its UV divergence is a minus B over epsilon because this adds up to 0. It's a fancy way of writing 0. OK. Now, I don't have any time to go into the details, but Sally mentioned for lambda phi fourth how the 1 over epsilon leads to a running anomalous dimension for the lambda coupling. And it's basically the anomalous dimension is A, or minus 2A or something. It's something like this. OK? So what has happened is the UV theory has some divergences, which are and anomalous dimensions, which are given by A. The EFT has a different set of anomalous dimensions, which are given by the minus B. So the anomalous dimensions of the two theories are different. But what's interesting is that the IR divergence in the full theory has been converted to a UV divergence in the effective theory. And this is related to what I mentioned last time, that the theory had logs of big M over little m, which when little m goes to 0, diverges. So this is an infrared divergence in little m. And we turned that into a log of m over mu in the matching plus a log of mu over m in the EFT. And this log of mu over m in the EFT, you can sum, and I'll explain what that means, by integrating the anomalous dimension in the EFT. We have no way of summing infrared logs using renormalization group equations. The whole renormalization procedure sums UV divergences. OK, but the EFT trick has converted an IR divergence into a UV divergence, which we do know how to sum. So we can sum all of these logs. And I will explain what that means in a second. OK, so this is one of the main applications of EFTs is to do these log resummations. And these are not small. Even in B physics, this is factors of 2. But if you're doing jet physics at the LHC or something, I mean, they can be factors of 100 or something. Your cross-section is just complete garbage without doing these resummations. And for those of you working on that, there's another terminology which works, which is people talk about Qcd factorization and so on. And there you have some hard scale of the collision, which you're factoring. So you write the cross-section as some hard cross-section convoluted with PDFs. And this is identical to the EFT. OK, the words are slightly different, but the mathematics is identical. And so if you do SCET, you will use one set of words. If you follow what other groups do, and you use what is called Qcd factorization, you use some different set of words. But there's a one-to-one matching. Everything's identical. It's really just a different language for exactly the same procedure. OK, so now let me give you an example of what I mean by this summation of logs. Yeah?
Is it guaranteed that IR divergences will sum up to a finite case?
If it's an observable, yes. If it's a measurable quantity.
Cross-section of the R ratio.
Yeah. So But hold on. OK, so this thing first came about in soft photon emission. So let's just, here there's a gluon. But the same thing happens if you do E plus E minus to mu mu and mu mu gamma. OK? And so why is there a problem is that if this photon has very low energy, you cannot detect it experimentally. OK, so I mean, you have to really think more like an experimentalist than a theorist. So you cannot tell mu mu from mu mu gamma if gamma, E gamma is less than some E threshold of your detector. So if you add this cross-section plus that cross-section where you restrict the photon to be soft, some E, then you get something finite. OK? And that's because you cannot distinguish these two processes from each other. But I mean, as a theorist, you might think you could. OK?
So if my E threshold changes, then I'm summing up different amplitudes.
So when you do the summation, this plus this with E less than E threshold, you will get a log of E threshold over whatever, the hard scale S, root S. The cross. So this is how people calculate jet cross sections. You have some energy for the jets and some opening angle, and you can get logs of the logs of the threshold energy. And well, if you use Sturman and Weinberg's jet definition, you'll get logs like this. And if you have collinear radiation, you can get logs of some opening angle, which defines a jet, and so on. So there's a whole technology of this. But the cross-section will depend on what the parameters are. And then LHC cross-sections depend on your jet definition, or what people call R, the jet R they use there. And you have to calculate that. Yeah. OK. So let me go back to the weak interactions. But let me do a non-leptonic process, which is B to C U bar D, which is, again, the same diagram, basically, B to C U to D. And now I have minus 4G Fermi over the square root of 2 VCB VUD star. And if you write down the possible dimension 6 operators you can get, which have 4 fields, 1B, 1C, 1U, and 1D. And they're left-handed because the weak interactions only couple to left-handed particles. You can write down 2 operators. So I'm going to write this as C1O1 plus C2O2. And O1 is C bar alpha gamma mu P left B alpha D bar beta gamma mu P left U beta. And O2 looks very similar, except the color in. So these alphas and betas are color indices. And here the color indices are contracted in a different way. So these are the 2 possible dimension 6 operators you can write down involving these 4 fields, which are QCD color invariant. And you can clearly see this is a W boson. So the B to C, the color of the B is the same as the color of the C. And the U and the D are equal. So at the tree level matching from this diagram is that C1 is equal to 1 and C2 is equal to 0. Because here you would have to do some color recombination. So in the EFT, this diagram turns into this dot. And there are 2 possible dots. There's an O1 dot and an O2 dot. But the coefficient of the O2 dot is 0. And the coefficient of the O1 dot is 1. Now, if you start doing radiative corrections in the EFT, for example, gluon exchanges like, well, I guess the one we want is really across here, you will find that this gives you a graph which is infinite and has 1 over epsilon poles. And the counter terms involve both O1 and O2, because a gluon running across here can transfer color from the C. This is a C, and that's a D. It can flip the color. You can exchange the color between the C and the D, and that'll turn O1 into O2. Yeah?
I think I just missed this, but the C1 equals 1 and C2 equals 0, that's at tree level?
Tree level, yeah.
Okay, thank you.
Yeah, so let's just say plus order alpha S. OK. So if you do the infinite parts of these diagrams, you find that mu dd mu of C1 and C2 is, well, alpha s over 4 pi. What is it? -2, 6, 6, and -2, C1 and C2. OK, so for doing this, you have to do the infinite part of the diagram, work out some. It's not that hard, but you can't guess this just by looking. OK. So you would just integrate this 2 by 2 equation, but in this particular case, it's convenient to define O1, O plus and minus as 1/2 O1 plus or minus O2, and C plus or minus is C1 plus or minus C2. And then, I guess it's gone up there, but C1 O1 plus C2 O2 is C plus O plus C minus O minus. And the reason for doing that is because this matrix is kind of nice and symmetric. So when you take these linear combinations, the two coupled equations separate. And you get, well, mu dd mu of C plus and C minus is alpha s over 4 pi. And then you get 4, 0, 0, and -8, C plus and C minus. So this is an example of just uncoupled renormalization group equations. OK, so let's put in the mu's. OK, so all of this is at a mu. This is at a mu. This alpha s is at the mu. So this tells you how you can evolve your coefficients from some starting mu to a final mu. So if you write C, any of these C's, at some final mu, in terms of the initial mu, you will find that you get terms which look like this one, and then you can get an alpha s, and now you have to decide what scale to put the alpha s at. And you could either pick mu I or pick mu f. Since it's on this side, I'll just call it mu I. And then you get a log of mu f over mu I. And there's some number here. And there's another number times alpha s mu I log mu f over mu I squared, and so on. And you get an infinite series of terms. And this is called the leading log series, which is basically summing terms which are alpha s times a log to powers n. That is, every alpha comes with a log. And you can get that just by basically, I mean, it's a differential equation. You can keep iterating and just take the first order approximation. The first order approximation would give me C is the initial value plus this alpha s times a 4 times a log of mu, because mu dd mu is like d log mu. And then you plug that back in and integrate one more time. It's just recursive integration. So this is what's meant by leading log resummation. And you can get it by integrating this anomalous dimension equation. So this is why integrating RGEs sum the leading log series. So this is called, so let me draw a table, actually. So you have a term which is 1. Then you have alpha log, alpha s squared, log squared, etc. So this is the leading log series. Then you can have alpha s squared log, alpha s times alpha s log whole squared, etc. So 1 extra power of alpha s. This is called the next to leading log series, and so on. Okay, so then alpha squared times alpha log. That's n2, NNLL, or whatever you want to call it, NNLL, and then people get tired and call it N3LL, etc. And this is called leading order. This column is next to leading order. This column is N2, NNLO, etc. So these are what the terms mean. And typically, the log can compensate for the alpha. And you have to sum the whole series. You can't just stop. So typically, people in QCD, I think they go to N3LL or whatever. So this is how you integrate them. And the one loop anomalous dimension and one loop beta functions, I'll explain in a second, give you this series. To get the next series, you need the 2-loop anomalous dimensions and beta functions, 3-loop, et cetera. OK, is this clear? OK. You have to do the infinite. You have to do the diagram. Yeah. I'm sure that's one of the homeworks in the Lesuche. So you just do that. Yeah.
So leading load is coming from only considering the one loop. So how can I make sure the leading load doesn't come from the two-loop level?
Well, you can just do this integration. So you will see that if you put in the 2-loop diagrams, they will contribute. There's basically one extra alpha without a log. So that's why then you would need an anomalous dimension, which is an alpha squared in it. So this, you can prove this, just that. You see, if you keep iterating this, every alpha comes with a log, because I mean, here, let's just do the, let's see how many boards I have. OK, so let's just do one of them, right? So I have, because I've decoupled the equations, let's just do, so this equation is actually very helpful. It's alpha over 4 pi is g squared over 16 pi squared. And then the 1-loop anomalous dimension is usually called gamma 0. So imagine I was integrating this equation. The way you integrate this is you also look at the beta function equation, mu dd mu of g of mu. And that's usually written as minus b naught over 16 pi squared. So that's the leading term in the 1-loop term in the beta function, g cubed of mu. And you divide the two. So you get dc dg is minus gamma naught over b naught c over g. OK, because the g squared over g cubed gives me a 1 over g. So if I put the c on this side and the dg on that side, you get d log c is minus gamma naught over b naught d log g, because d log c is dc over c, et cetera. And so integrating this tells me that c of mu1 over c of mu2 is alpha s at mu1 over alpha s at mu2 to the minus gamma 0 over 2b0, because the alpha goes like g squared, so I put an extra half in there. OK, so this is the solution of the renormalization group equations. And if you start expanding all of these in terms of one scale, you will get the leading log series. And in the case of B quarks, or the B physics result, I started with, it's gone now, but C1 was 0, C1 was 1, and C2 was 0. So C plus was equal to C minus. I integrate them. And C plus and C minus have different anomalous dimensions, so they're no longer equal. And then I can undo this calculation and get back C1 and C2. So I'll leave this as a numerical exercise, but you find that C1 of MB is 1.12, and C2 of MB is minus 0.27. OK, so this started at 0 at the weak scale, but it's no longer 0 at the low scale, and there's a 30% shift from the integration. And you can also compare alpha s at mz, which is 0.118, and I don't know. It used to be 1184. I'm not sure what the next digit is. And by integrating the beta function equation, you can find that alpha mb is 0.22. OK? So there's a factor of 2 change in the couplings. There's no sense in which this difference is perturbative. And that's because the alpha log, the log and the alpha together are order 1. And that's why you have to do these leading log resummations. And as I said, in LHC cross sections where the hard scale is TeV and the jet scale may be 20 GeV, you can get factors of 100 from the NLL resummations and so on.
I have a question.
Yeah, 1 second, I think. Yeah, that's all I want to say on this. OK, so this, yeah.
Thanks. Where did your mu dg d mu come from in that second one?
That's the beta function equation. So this is how the coupling constant runs in a gauge theory. Yeah, so this, I don't want to go through the field theory of that. But yeah, so this is mu dg of mu is beta of g. And the one loop term is g cubed. And the famous minus sign here is what the Nobel Prize for Politzer, Gross, and Wolczek was about. OK, other questions? OK, so yeah.
So when you say C2 is 0, at what scale are we saying that?
No, so at the starting scale. So C1 at MW was 1, and C2 of MW was 0. The scale at which you did the matching, where we integrated out the W boson. This one. We went from here to here at the scale MW. And so, yeah, so this is at MW. So those are the starting values. Because remember what we did last time, there are no large logs, and perturbation theory is valid, provided mu is at the mass, mu is comparable to the mass of the particle being integrated out. So in the weak interactions, you traditionally either match at MW or MZ, whichever you, one of the two, and then there are no large logs. So this is order alpha S without any big logs in them. It's just an expansion in alpha S at MW. And all the logs from MW over MB are coming from these, integrating these equations. Yeah?
If I can understand, the 4 and the -8, those would be anomalous dimensions of C plus and C
Yeah. And this, because, so in general, you'll get some 2 by 2 matrix. This is sufficiently simple that, taking O1 plus O2 and O1 minus O2 diagonalizes them. Otherwise, you have to take some other, you have to diagonalize the anomalous dimension matrix or numerically integrate the 2 by 2 coupled equations. All right. OK, any other questions? OK, this is the whole renormalization group improvement of any quantity. It's basically this. I mean, it's summarized here. All the other calculations are just versions of this, where you need the anomalous dimension of the whatever object you're looking at. Yeah.
What do we gain from the diagonalization, given that alpha itself is also running there?
Oh, you just decouple. Instead of having two coupled equations to integrate, you have two separate decoupled equations.
I guess we'd be using leading logs either way, right?
Yeah, they're both. No, this is just a way to do the integration analytically.
Okay.
There's no difference. I mean, if you have a way of integrating those, the answer is the same as this. Yeah. OK. So OK, any other questions? OK, so as I said, there's some miscellaneous points which I might want to wrap up. So the other one is on integrating out heavy or decoupling of heavy particles. So imagine you were doing QED, and you looked at a one-loop correction to the photon propagator. You can show from gauge invariance that this has to equal something which is p nu minus p squared g mu nu, this transverse projector, so that if you dot it into p mu, you get 0, times what's called pi of p squared. So this is the vacuum polarization function. And pi of p squared is e squared over 2 pi squared, 1 over 6 epsilon, minus the integral 0 to 1 dx, x. OK, you can look this up in Peskin and Schroeder. I think it's done explicitly. So that's just the one-loop diagram. Now, from the infinite part, so this is a UV divergence. From the infinite part, you need a counter term. From the counter term, you calculate the anomalous dimension, in fact, the beta function. And you find that mu dE d mu is minus e cubed over 12 pi squared. So this is the one-loop beta function from QED. Now, we're using MS bar, which is what's called a mass-independent subtraction scheme. And this is just e cubed over 12 pi squared, no matter what the mu is. So this fermion could be 5 GeV, or it could be the gut scale. It's still minus e cubed over 12 pi squared. Yeah? No, it's not, of course. Yes, e cubed over plus e cubed. Sorry, it's not asymptotically free. Yeah. Plus, yeah. So you might, your intuition would tell you that gut scale particles shouldn't be contributing to vacuum polarizations at a few GeV, right? We're supposed to have decoupling. There's a theorem by Appelquist and Carozone which claims that there's decoupling. And there's a related problem, which is if I look at the finite part of pi of p squared, because this is canceled by the counter term, which leads to the beta function. The finite part has this log in it. And let's just say p squared is small. But there's a log of m over mu. And again, if m is the gut scale and the mu is small, this is a huge log. And what's happening is you've made two mistakes. You're integrating with the wrong beta function, in quotes, the wrong beta function. So you're getting the wrong coupling at low energy as you evolve in mu. And this is compensating from that by putting in a large log to cancel the effect of your wrong beta function. Now, the reason the Appelquist-Carozone theorem doesn't apply here is that they proved something in what's called the momentum space subtraction scheme, where particles decouple and the beta function has some different form. And I explained that a little bit in the Jesus lectures, but I won't do that here. So what people did when they started calculating in MS bar, well, I think Weinberg was the first to do this, was you have to explicitly integrate out the heavy particle. So you have a theory. So here's m. In the theory above m, you have this, whatever you want to call this. Okay, so some dynamical heavy field with a mass. So you have the psi field, or a heavy field, this one, and some light fields. So let's just pretend this is the top quark or something. So you have all the particles of the standard model. And then down here, you drop the top. So you have all the light fields. But you don't have this one field is gone from the theory. Now, OK, so we discussed this as a matching calculation before. So what is the matching calculation? You look at the 2-point photon propagator. And this is the tree level diagram. And then you add this diagram. And here's the diagram. Okay, well, I can write it one more time. But it's basically just this just this. This is canceled by the counter term. And I'm left with the finite part. And I'm doing the matching now at mu is order m. So this log can be written as log of m squared over mu squared plus log of probably 1 minus p squared over m squared x1 minus x. OK, just factoring out this piece. So what do we do in the EFT? We have some external momentum p. And I'm expanding in p over m. Here's my pi of p squared. It's got this e squared over 2 pi squared, et cetera. So here, OK, so pi of p squared. And there's a, well, OK. It's this, and then there's no room. But there's also a minus sign and an integral dx x1 minus x of this whole expression. So what does the first term do? It gives you a correction to the photon propagator proportional to p nu minus p squared g mu nu. This is simply the Fourier space version of f mu nu squared. It's two derivatives and two gauge fields, because you can stick two a's here. And if you, so it shifts the kinetic energy term of the photon, and you have to renormalize the, so you get some contribution. This was minus a quarter. And you get some contribution 1 plus something, which is basically e squared over 12 pi squared or something, because the integral of x1 minus x is a sixth. So you rescale the photon field by whatever number you get here to put it back as minus a quarter. When you do that, what was a gauge coupling, E psi bar A slash psi, gets, if this factor is some r squared, you would rescale the photon field by r. The r would go down here. The coupling gets shifted, basically, by exactly this, well, the square root of this factor. And let me just write, do I have my, did I not pick up the relevant notes? OK, so the, so if you, and you can do a sort of a geometric series, because you can sum 2 of these and 3 of these, et cetera, because they're all you're just multiplying the diagrams together. So you get a 1 over 1 minus pi. And if you work it out, you find that E squared low at mu is E squared high at mu minus 1 over 12 pi squared log m squared over mu squared. So what you find is that the theory without the top quark has what's called a threshold correction. The coupling constant switches from the value in the theory above the top quark plus this extra term. And there's no big log here, because in fact, if I integrate it out at mu exactly m, the shift would be 0, but I don't have to pick exactly m. So this is what's called a threshold correction. And the coupling in the EFT is different. Gauge couplings in the EFT differ from those in the high energy theory by these corrections. The similar thing happens to the gluon coupling, et cetera. Now, this also explains something which I commented on about fields in the EFT are different from the fields in the full theory. Because once you've gone to the EFT and rescaled, just this first diagram in the EFT on the low energy theory includes the top quark loop in it. So what if I call this A, let's call this A heavy, the A heavy 2-point function plus the heavy 2-point function with the top quark loop is the same as the A light 2-point function. So this A light in it has some TT bar pairs in it. And you can be even more precise here. You can take the EFT Lagrangian and take derivatives with respect to the top quark mass. Say, let's call this top. Because the coupling in the effective theory depends on m top. And you can calculate, if you take the full theory and you differentiate with respect to the top quark mass, the action, or the Lagrangian, has a minus mt t bar t. So when I'm doing a path integral, e to the is, and I do d by d, if I do d by d m top, I'm basically getting an insertion of minus t bar t. Okay, because I'm just differentiating the exponent, I get back this in the, so I'm getting a, whatever. There's some Green's function with stuff here, and I get the same Green's function with an extra t bar t. So you can calculate matrix elements of t bar t in the EFT, even though there's no top quark anywhere, through this procedure. And this is kind of interesting. People have looked at what Sally talked about the Higgs, the glue to Higgs coupling through a top quark loop. And by using tricks like this, you can calculate these matrix elements to, I forget, at least n2 whatever, n2ll, by using some trickery like this. But this is what I mean by the EFT fields are not the same as the full theory fields, because you've done some non-trivial connection between the two. If I now take the log of
Can I ask you a question? I was just wondering, could you just repeat what the first one was here, when you calculate an amplitude involving?
So if you took an amplitude involving some EFT fields, and I take d by dmt of it, well, let's first do it in the full theory. Some full theory fields and d by dmt of it. The full theory Lagrangian has mt t bar t in the Lagrangian, so when I differentiate with respect to mt, I get an insertion of t bar t. I can repeat the calculation in the EFT. There are no top quark fields in the EFT. However, all the couplings in the EFT, like the gauge coupling, have an implicit, there has an MT in there. So effectively what I'm getting is I'm getting a d by dE times dE dMT. And I know what dE by dMT is, I just differentiate that. And so you get something non-zero. And in fact, you can use this to match the T bar T operator from the full theory to the EFT in terms of without having to do some other calculations. And this is used for the Higgs calculation. OK, if I take the log 1 minus p squared over m squared x1 minus x, I can expand it out. So the log of 1, because p over m is small, the log of 1 is 0. And then I get minus p squared over m squared x1 minus x plus dot, dot, dot. And then I still have the overall minus dx x1 minus x times this whole thing. And so what you're getting is an operator with two derivatives, an extra p squared over m squared, and then the x1 minus x turns into an integral of x squared 1 minus x squared, et cetera. And if you work out this factor, this leads to an operator in the EFT, which is e squared over 240 pi squared m squared d alpha f mu nu d alpha f mu nu. So the e squared over 2 pi squared just came from the prefactor in front of the diagram. The 1 over m squared is here. The p squared turns into these two extra derivatives on the f mu nu. And then this 240 is just coming from integrating the x squared 1 minus x squared. So you can check that that gives you this. And then the next term would give me another d beta, and so on. So here's another. You can do the matching, if you want, to higher order. Yeah.
About the T bar T, could I do this calculation within the EFT by assuming some heavy current or something?
Well, you have to know how the EFT parameters depend on mtop, though.
Like, is there an alternative way of calculating the scattering amplitude within or the correlator within the EFT?
Well, the EFT doesn't have the top quark field in it, so you can't. That's right. But there's a trick. This trick allows you to do some things. Well, not too many things. It allows you to do T bar T, because that's what the operator was in the full theory of the mass. If you wanted T bar T whole squared or something else, you can't, because there's no parameter to differentiate to bring down that operator. All right. OK, so that's one thing I wanted to make, one point. And the other point I wanted to make, let's see if we can get this to work, is, yeah.
In the case where you start with a full theory and you build the EFT,
Yeah.
it's clear what you can get, right?
Yes.
But what about cases where you think you have an EFT like GR, and you don't know what the full theory should look like? Is there a way to identify elements of the full theory by being able to tell the things that you can actually get from the EFT?
I don't think so. Yeah. So it sort of goes one way. You're losing information by going to the EFT. Yeah. OK. So probably the last point I want to make is field redefinitions, which is another source of confusion. So I'll just do this in the context of scalars, just so I don't have to keep writing too many things. But it obviously works with fermions, gauge fields, and everything. So imagine I have some action, which is a function of phi, and I change variables. So I let phi become some function of phi. So for example, phi goes to, I replace phi by phi cubed over m squared or whatever. OK, just here's an example. Then s of phi becomes S of f of phi, which I'll call S prime of phi, a new action, given by changing variables in the old action. Now, how do I calculate S matrix elements and so on? I calculate z of j, which is some functional integral d phi e to the I s of phi plus j phi. I differentiate with respect to j to bring down factors of phi. I calculate the Green's functions, and then I do the LSE reduction, whatever. There's some, however you calculate your cross sections. Now, a functional integral in the end is just an integral. There's no operators, there's no quantum mechanics. It's just a big fancy integral. I can change variables in an integral. You've done this in calculus. So this gives me, if I make this change of variables, I get a d phi. I get the Jacobian of f with respect to phi, the if I'm integrating dx and I have x as f of w, then dx is f prime of w dw. Okay, that's this Jacobian. And then I get phi, s of f of phi, plus j f of phi. Okay? Now, in field theory, except for the anomaly, in all other cases, at least in dimensional regularization, this Jacobian is 1. It's some, at least when you're making local changes like this. You get some determinant of something which is so singular that it's 1 in dimensional regularization. So I'm going to ignore that. Yeah?
Could you explain a bit more, please, why it should be 1 in different?
No, I'm not going to do that. Yeah, you just got to, there are ways to calculate these functional determinants, and if you do it, essentially with zeta function regularization or whatever, you just get 1. And it's again because there's no scale and it can't do it. I mean, there's nothing it can be, basically. It has to be a pure number, and it's 1. OK, now suppose your friend was given this other action, and they started calculating. What would happen is you would calculate z prime of j. Maybe I'll use twiddle here so it doesn't look like a derivative. I think it's better. Z twiddle of j, which is the integral d phi e to the I s of f of phi, or s twiddle of phi, plus j phi. They have the new action, and you're adding the source. Maybe I can call this j twiddle, just to, OK? Now I go do the LSZ reduction, and I calculate cross sections. OK. So I know that my original calculation of cross sections with the action S and the field phi for Green's functions is the same as the cross section calculated with S of f of phi. And Green's functions are insertions of f of phi, not phi. OK, I calculate f of phi 1, f of phi at point x, f of phi at point y, et cetera. Wherever I would have done Green's functions of phi, I do f of phi instead. And they're equal, just because it's a change of variables. The other way of calculating is to use this action with insertions of phi. They're clearly different. So the Green's functions and so on will change when you change variables. However, and this is the key point, the LSZ formula says that when you go calculate S matrix elements, it doesn't matter what operator you use to create the particles. So this calculation used the operator phi to make the particles. This calculation used the operator f of phi to create the particles. The LSZ formula says that both S matrices are the same, because the action's the same. I used a different operator. It doesn't change the S matrix. So when you make a change of variables like this and use a new action, the Green's functions will change, but the S matrix stays the same. Okay, is this? So I can make a change of variables in my action, and I will keep the same S matrix. So the actions are equivalent as far as anything observable is concerned. Okay, so why do we not normally do this in a field theory is that we have Lagrangians, and we restrict our terms to d less than or equal to 4. Now suppose I made a change of variables like this. Well, I don't want to introduce any dimension 5 or 6 operators. I already have a phi to the 4th, let's say. So whatever change of variables I make on phi can't change phi to some phi squared or something. I'd go beyond dimension 4. So if you restrict yourself to theories where the operator is a dimension less than or equal to 4, the only thing you can do is you can let phi I go to some Cij, phi j. You can just make some kind of linear transformations. And even though you may never see this in a field theory book, you really are doing this implicitly, because you're always making sure your kinetic term is 1/2 d mu phi I, d mu phi I. It's diagonal with 1/2. And so really, you can have an arbitrary symmetric matrix here, and you diagonalize it and rescale the field. So implicitly, you are doing this. And in the weak interactions, when you start doing radiative corrections, you can get off-diagonal terms in the fermions from CKM angles, and you always rediagonalize the kinetic energy terms. Yeah?
So if you redefined your field such that you had operators with dimension greater than 5 in your Lagrangian, would you still get the same observables out?
Yeah. So that's what yeah. Okay. So normally we don't see, but in an EFT, where you don't have this restriction, you can make arbitrary field redefinitions. And typically, you want to make sure you respect the power counting. So you make sure you put the same m as your expansion parameter m in this. So here, if my EFT expansion is m, I would put an m down here to make sure that the field redefinition respects the power counting. Yeah?
If I take this for non-radical theory and I do this field redefinition and introduce dimension 5, 6 in the same terms, would it still be renormalizable, or would it?
It would be still renormalizable. You may not notice it if you calculate it, but it is renormalizable. And in fact, in one of these papers with Rodrigo Alonso, we looked at the linear sigma model, which is a renormalizable theory, but in the exponential parameterization, like a Goldstone boson, and showed that the counter terms all still work. Yeah, you can do it. But this allows for some freedom. And people sometimes refer to this as using the equations of motion. So what happens if I make a change of variables like this? So let me just say I go phi to phi plus, I'll just call it delta phi. It's not small, really, but we'll. So here's an example. This is delta phi. Oops. Phi. So the action goes to the action of phi plus delta phi, which is the action of phi plus delta s delta phi plus 1/2 d2s d phi squared delta phi squared, etc. But the first order term, this is the classical, it's important, it's the classical equation of motion. Because that's what the Euler-Lagrange equation is. The delta s delta phi equals 0. So what this tells you is that in a field theory, at least to lowest order, you can use the classical equations of motion to simplify terms in a Lagrangian. However, you have to be a little careful. So this is it's only true to first order and delta phi. The correct answer is that you have to keep the entire expansion. So for example, in the let's just do the Higgs, but forget the gauge field. So you have d mu h dagger d mu h minus lambda h dagger h squared. And then the mass term I'll write as plus 1/2 mh squared h dagger h. Because if you go to the broken phase, this thing becomes the physical mass of the Higgs. It has the opposite sign. You have symmetry breaking, et cetera. So this is just another way of writing the VEV. Now let's suppose h goes to h plus xi something, and I want it to be, so if I gauged it, I wanted to have the same quantum numbers as the Higgs, and so the natural thing to do is to do something like h dagger h times h, keeps the same, it's the hypercharge 1/2, SU2 doublet, et cetera. Then what happens here, so let me just call this delta h, oh, sorry, there's a 1/m squared here. Then from this, you're going to get L goes to L plus d mu delta h dagger d mu h plus d mu h dagger d mu delta h plus d mu delta h dagger d mu delta. OK, I'm not going to write everything down. So let me just stick with the mass term. Delta h dagger h plus h dagger delta h plus delta h dagger delta h. OK, I can do this. Is this clear? I just plug this in. Forget the lambda term for the moment. I mean, I can also write, you can also do it, but I don't want to keep writing. And this is in the action. So there's an integral here. So I can integrate by parts on these first two terms. And this is minus delta h dagger d squared h. And this is minus d squared h dagger delta h. And then I get all of this other stuff. OK, so if I look, so now let's suppose I do this calculation where this c delta h is this quantity. And so it has a 1/m squared in it. It's effectively adding a dimension 3 contribution to the dimension 1 operator. So all of the terms with one factor of delta are dimension 6. So all of this stuff is dimension 6. This term is dimension 8 because there are 2 delta h's. And then again, this stuff is dimension 6. And this stuff is dimension 8. If I look at the dimension 6 terms, I get, you can see I'm just getting the classical equation of motion. I'm basically getting delta h times whatever. OK, so you get minus delta h dagger d squared h plus a half mh squared h plus whatever the lambda term is plus Hermitian conjugate. And this is the classical equation of motion for the Higgs field from that Lagrangian. So suppose your Eft Lagrangian, whatever it was, happened to have the operator. OK, so let me just actually finish this with, and now I plug in this thing for delta h. So this term is minus c over m squared h dagger h dagger d squared h plus a half mh squared h dagger h plus blah, blah, blah. And the Hermitian conjugate just doubles it, makes it 2 there, but OK, it doesn't matter. So suppose my Eft Lagrangian at dimension 6 happened to have the operator h dagger d squared h with some number, CEOM. If I pick C correctly, I can kill this. So there's a 1/m squared here. So if I pick C equals minus CEOM, then by making the change of variables, this exactly cancels this operator. So I can remove this from the Eft. The price of that is I induce terms which are, so C is minus COM, so I introduce CEOM over m squared times h dagger h squared times 1/2 mh squared. And then the Hermitian conjugate will get rid of the half. And I believe the lambda term will give me minus CEOM over m squared. I think it's 4 lambda h dagger h cubed. OK? Yeah?
Or should it be
Squared. Yeah. OK? So you can trade this dimension 6 operator for a shift in the lambda phi fourth coupling proportional to mh squared c over m. And then this operator, the h dagger cubed operator in SMEFT, is called c sub h. You can shift c sub h to c sub h minus c EOM over m squared. And an example of this from the old days is that the penguin diagram, which produced an operator which was psi bar gamma mu ta psi d mu g mu nu a. So that's, again, coming from this diagram. You can replace this by the equations of motion to be psi bar gamma nu ta psi. And you get a 4 fermion operator from it. So you can replace the so-called penguin operator by a 4 fermion operator. But this is not the same as just using the classical equations of motion. You're really making a field redefinition. And if you go to dimension 8, you have to keep these ordered, these delta h dagger, delta h terms. You have to keep all of this stuff to make the correct transformation. So this equation of motion business is like a sloppy thing at lowest order. The correct way to do it is to make a field redefinition. And maybe I'll put this on the wiki too. I have a paper from 1997 where we're doing heavy quark effective theory to 1 over m cubed, where you have to keep this, up to 3 orders. You have to keep this, make these field redefinitions to get it correct. OK, so now I can, since Sally's going to talk about SMEFT, I can just explain briefly what that is. So actually, hold on. Any questions? Yeah.
So when you trade out these higher order operators for a field redefinition, you're going to get the exact same phenomenology, right?
Identical. S matrix, yeah. Green's functions will change. And in fact, in the old days of heavy quark effective theory, there was like some discussions where 2 different groups had different Lagrangians, but all the physical observables were the same, and it turned out that they were using different. One was a field redefinition of the other.
And to get the exact same values, would you have to do that expansion at the top there to all orders?
Well, so we're doing an EFT, and you have to decide what order you stop at. So you just work to whatever order you want. So typically in SMEFT, you would work to dimension 6, and then you wouldn't have to worry about all the dimension 8. There's some work done on dimension 8. So if you're going to keep dimension 8, then you have to keep these quadratic pieces. There was another question? Yeah.
So how arbitrary are these only considered like 5 plus the 5?
They're kind of arbitrary. You want to make sure that you maintain locality of the Lagrangian, et cetera, so you don't go into some mess. But I could add to the Higgs field. I could add, psi bars. If I can write something which is a scalar, a Lorentz scalar, weak doublet with hypercharge a half, the same quantum numbers, yeah, I can do that. I can mix fermions and scalars and everything, yeah.
So, but you always have to keep,
Well, because you're making shifts which are, in some sense, higher dimension operators. So yeah. Mm-hmm. Yeah.
So you're still kind of sticking with like some order of polynomials. You can't do exponentials with the ancient stuff.
Well, I mean, it's possible, but in the EFT I don't know. But in the EFT context where everything's been expanded in M, you're treating this also like an expansion in M. But what it means is that you have less parameters than you might have thought, because there are some operators which can be eliminated.
So in this kind of field redefinition where I can take delta phi is small, so can it be
I wouldn't say it's small. It's just it's high order in the power counting. It's not. I wouldn't say it's small.
But in case it is small, can it be argued that it's similar to looking at fluctuations around a classical background, and in that case keep only the delta phi linear order terms and neglect all the higher order?
Sort of. I mean, it's related to that. That's why you get the classical equation. But But OK, I want to emphasize, this is a classical equation of motion, but we're in the complete interacting quantum theory. OK, this is true to all orders. I do not modify the equation of motion by quantum corrections, because it's just a field redefinition, and you're just doing a path integral. I mean, it's literally a change of variables in an integral. OK. So, all right, we'll try and finish. So what do you do in SMEFT is well, first of all, SMEFT is kind of a fancy name for what you might just call the standard model. Because, I mean, it has a long history of higher dimension operators. But the reason the name came in is because there's something else called Higgs effective theory, which is a little bit different. I don't want to discuss it. We have no time. And so it was just to distinguish two different versions of electroweak symmetry breaking. So we take the standard model gauge group, SU3 cross SU2 cross U1. You take the standard model fields, the Higgs, the quark doublets, the lepton doublets, et cetera. And you construct all possible operators you can have, gauge invariant, Lorentz invariant, et cetera. And then you remove total derivatives. You can drop because you're in the action, so something which is the integral d mu of some function, that's just 0 in the action. So you can drop that. And 2, you can make field redefinitions. And typically what you do is you try and eliminate as many terms with derivatives as you can. So typically you will eliminate things with d squared on the Higgs or d slash on a fermion. And by making the field redefinition, you remove them and you get to other quantities. So that's how the Lagrangian is constructed. And I need the counting, but let's see if I can find it. OK, now the original dimension 6 was Buchmüller and Wheeler from 1986. They had a few extra operators. They missed one operator. It took from 1986 to 2010 to get the Lagrangian right. That is just the list of operators, right? It turns out that at dimension 5, if the number of generations is 1, so these quarks and leptons have some generation index. If you ignore that, there's one delta L equals 2 operator. There's one of these plus its Hermitian conjugate. If the number of generations is 3, you get 6 plus the Hermitian conjugate. So this is that Weinberg operator I talked on, which gives a Meyer on a mass. If you go to dimension 6, you have baryon and delta B equals delta L equals 0. Baryon and lepton number conserving operators. And there are 76 Hermitian ones. People sometimes talk about 59 and so on, but then some are complex and whatnot. So the 76 Hermitian, and if the number of generations is 3, which is where we are, there are 2,499. And there are delta B equals delta L equals 1 operators, and there are 4 here plus Hermitian conjugate. All right, what is it? 273, I think. 273 plus Hermitian conjugate. So this is the classification. And I think people have classified all the operators at dimension 8 as well. So since this is going to be discussed tomorrow, I won't write down what all the operators are and the structures and so on. But now, if you want to look for deviations from the standard model, there are 2 sort of ways which people do it. One is take somebody's BSM model and compare with the data and make plots of what's excluded. The other option is if you believe that there's no new physics near the weak scale, and typically our effects go like P over M squared. So if this is the Z or whatever, and you're at a TeV, you're starting to get to 1%. So if you have no new particles at a few hundred GeV, you can use the Eft expansion. Then what you can do is you can fit to these parameters. And you have some region. And then if somebody has a model, they can go calculate what the Eft parameters of the model and see if it lies in the allowed region or not. So this is in some sense a model-independent way. You don't care where the theory came from. The only assumption is that there are no dynamical particles involved at the scales of the experiment. So people are trying this. The problem, of course, is it was non-trivial, by the way, to count. You can try counting this and see if you can get it. So the standard group theory methods to count invariance, it doesn't quite work because we also have to add these two additional factors in. And so, I mean, this was worked out by Xiaochan Lu, Tom Melia, Brian Henning, and Hitoshi Murayama, it turns out this is related to operator counting in a CFT. So you can count the number of invariants. Once you know there are 2499, now you have to write them all down and contract indices and make sure they're independent, which is also a bit of work. But at least you know whether you got them all or not. OK, question?
Is the purpose of the field redefinition just to make the math easier?
Well, they're redundant operators. So I mean, it's hard enough with this many, right? If you have another 500 more, you want to get rid of them. Nothing will depend on them. So if you were then trying to fit to experiments, you'd have flat directions because there'd be certain linear combinations. No cross-section depends on those. So you want to eliminate as much redundancy as possible. Yeah. OK. Any other? I think I'm out of time anyway. But any other questions? Yeah.
Do you happen to know what paper they wrote to get all of those?
Which ones?
I guess how they counted all of these things.
Well, this one's a paper I wrote, this one, with Rodrigo Alonso, Elizabeth Jenkins, and Mike Trott.
That one's an Einstein, but I meant the other one you were talking about, this, the one where they actually first worked it out. And I thought you were saying.
Oh, no, the CFT calculation. That was done later. But I think that has a title like 2, 4, 32, whatever. I mean, look up like Tom Melia and a bunch of numbers in the title. He has several papers like this because it's kind of fun stuff to do once you get into it. But and there's a Mathematica code which you can download, which will tell you how many operators there are. And the public version goes up to about dimension 8 or 10. I mean, 8 or 10, I think, maybe 10. And then he has a secret code which goes up to 25 or something. Yeah.
The state series method, does it only give me the number of operators, or can I generate the operators?
You cannot generate the operators. And so people are trying. So what it does do is basically you construct a polynomial. So it'll tell you that you have, let's say, Higgs to the, Higgs squared, quark cube. I'm just making something up, right? A lepton, whatever, U. And there are 7 operators with these fields in it. It'll tell you that. But then you have to construct the indices and make sure that whatever you constructed are linearly independent. So this is basically, I mean, Weil has a formula for group invariance, which, there's a Weil character formula which will tell you how many invariants you have at any order. So that's the first step. But then these are these 2 additional things which math people wouldn't care about, and you have to include those as well. So you're essentially using the character formula, but using the characters of the conformal representation. And essentially, because d squared h equals 0 is like the condition for the thing to be a primary operator. And so that's what's happening. Yeah, it was a very nice result. OK, but it was done correctly, OK, for this. But it took 25 years to do it right. Other questions? No, here there's a counting, right? So.
Oh, the previous one was just listing.
Well, I mean, there's systematic. You write down the invariants, work out what the possible equations of motion are. It was not a guessing thing.